Why does AI use so much power? The basic answer is simple. An AI response is not pulled from a finished list of answers. It is manufactured in real time by specialized computer chips performing an enormous number of calculations, then doing it again for the next word, the next image, the next user, and the next request. The electricity does not only power the calculation, it also moves data between chips, keeps thousands of machines synchronized, removes the heat they produce, and keeps the entire facility ready when demand suddenly rises. A single prompt on a phone may look almost weightless. Somewhere else, however, that prompt enters a building filled with servers, electrical equipment, cooling systems, network switches, batteries, and backup generators. The answer appears on your screen in seconds. But behind it is a physical chain of machines turning electricity into computation. To understand where the power goes, follow one prompt through that chain. The first important point is that a modern AI model is not a traditional program with a neat rule for every possible question. It is a neural network, which is a large mathematical system trained to recognize patterns. Inside it are billions of adjustable values called parameters. You can think of them as tiny numerical settings that shape how strongly one pattern influences another. During training, the system processes example after example, makes a prediction, measures how wrong it was, and adjusts those settings slightly. That cycle is repeated across massive collections of text, images, audio, code, or other data. The model is not storing a simple answer key. It is gradually building a statistical structure that can produce useful outputs from new inputs. That training process is power-hungry because the same core calculations are repeated an extraordinary number of times. A large model may be spread across many accelerators, which are chips designed to perform huge amounts of math in parallel. Graphics processing units, or GPUs, became central to AI because they can run many similar calculations at the same time, instead of handling them mostly one after another. One accelerator can draw hundreds of watts under heavy load. An AI server may contain several of them, along with processors, high-speed memory, networking hardware, and fans or liquid cooling equipment. Then thousands of servers may work together on one training job. The power of AI does not come from one unusually intelligent chip. It comes from coordinating a very large number of fast chips for a very long time. But raw calculation is only part of the story. The model's parameters must be available while the chips are working. That means enormous volumes of numbers are constantly being read from memory, moved into the computing units, combined with new data, and written back. Moving those numbers costs energy. In modern AI systems, the distance between a calculation and the data it needs can matter almost as much as the calculation itself. This is why AI hardware is built around extremely fast memory and high bandwidth connections. High bandwidth simply means the system can move a large amount of data every second. The faster the chips calculate, the more urgently they need fresh data. If the data arrives too slowly, expensive processors sit underused while still consuming power. If many chips need to exchange information, the network between them also becomes part of the energy bill. There is a useful comparison here. A chef can work quickly only if ingredients keep arriving at the counter. 1,000 chefs do not help if they spend most of their time waiting for the same refrigerator door. AI systems face a similar problem, except the ingredients are numbers, and they must travel through memory chips, circuit boards, cables, and network switches at remarkable speed. So the first major reason AI uses so much electricity is not simply that it performs a lot of math. It performs a lot of math while moving a lot of data across a large machine. Training gets most of the attention because it can concentrate enormous computing demand into one project. Yet, training is not the only stage. Once a model is deployed, it enters inference, which is the process of using the trained model to generate an answer, classify an image, recommend a video, translate a sentence, or make another prediction. Inference can be far smaller than training for one individual request. The scale changes when a service has millions of users. Every new prompt activates the model again. A text model usually generates an answer one small unit at a time. Those units are called tokens, which may be a word, part of a word, or punctuation. Each new token requires another pass through much of the model, while the system also keeps track of the conversation that came before it. A longer answer, therefore, requires more work than a shorter one. A longer conversation requires the system to process more context. Asking a model to inspect a large document, reason through many steps, create an image, or generate video can require substantially more computation than a brief text reply. There is no single honest number for the electricity used by one AI question. The result changes with the model, the hardware, the length of the prompt and answer, the number of users sharing the system, and how efficiently the data center is operated. That uncertainty matters. It is easy to produce a dramatic estimate for one query and repeat it as though every request were identical. They are not. The more useful question is what happens when variable demand is multiplied across billions of interactions. At that scale, efficiency becomes complicated. AI providers try to combine several requests so the hardware stays busy, route simpler tasks to smaller models, reuse parts of earlier calculations, and reduce the numerical precision used inside the model. Lower precision means representing numbers with fewer bits when the task can tolerate it. This reduces memory use and lets the chips perform more work per unit of electricity. Smaller models can also handle many everyday tasks without activating the largest system available. Specialized chips can be designed around the operations AI uses most often. Software can skip unnecessary work, compress a model, or send each request to the least expensive system capable of answering it well. These improvements can sharply reduce the energy required for one result, but they create a second effect. When AI becomes cheaper and faster, people use more of it. A tool that once generated a paragraph may later analyze an entire company archive, operate continuously as an agent, create thousands of images, or support real-time video. Efficiency lowers the cost of each task, while new uses increase the number and size of tasks. That is why better chips do not automatically guarantee lower total electricity use. They can reduce energy per answer and still contribute to higher overall demand. Now return to the data center. Because the processors are only one part of the building. Nearly all the electricity entering computing equipment eventually becomes heat. If that heat is not removed, the chips slow down, become unstable, or shut off to protect themselves. Traditional data centers move large volumes of air through server racks. Higher density AI systems increasingly use liquid cooling, bringing coolant close to the hottest components so heat can be carried away more efficiently. Cooling itself requires pumps, fans, chillers, heat exchangers, and sometimes cooling towers. The facility also loses some energy while converting and distributing electricity. Network equipment carries data in and out. Storage systems hold model files and user data. Batteries and uninterruptible power supplies protect the machines from short interruptions. Backup systems remain available because a momentary power failure can interrupt expensive workloads or affect millions of users. Engineers measure this overhead with a number called Power Usage Effectiveness, or PUE. It compares the total energy used by the facility with the energy delivered directly to computing equipment. A perfectly efficient building would have a PUE of 1, meaning every unit of electricity goes to the computers. Real facilities are always above 1 because cooling, power conversion, lighting, and other systems also consume energy. This reveals the third major reason AI uses so much power. The model does not run in isolation. It depends on an industrial system built to deliver electricity reliably, move heat continuously, and remain available every hour of the day. The scale of that system is now large enough to affect power planning. According to the International Energy Agency, data centers worldwide used about 485 terawatt-hours of electricity in 2025. A terawatt-hour is 1 billion kilowatt-hours. The agency's central projection puts data center consumption near 950 terawatt-hours by 2030, roughly double the 2025 level. Not all of that electricity is used by AI, but the IEA expects electricity use from AI-focused data centers to grow much faster and roughly triple over the same period. Those global numbers can hide the local problem. Data centers are concentrated in specific regions, and a single large campus may request hundreds of megawatts of continuous power. The challenge is not only generating enough electricity over an entire year. The grid must deliver large amounts of power at the right location, at the right moment, through transmission lines, substations, transformers, and other equipment that can take years to build. This is why the AI power debate is also becoming a grid debate. A country may have enough annual generation on paper, while a particular city lacks the local wires and substations needed for another high-density computing site. New data centers can compete with factories, homes, and other large users for limited grid capacity. They can also encourage investment in new generation and infrastructure, but the timing, cost, and source of that electricity matter. The environmental impact therefore depends on more than the number of kilowatt hours. It depends on where the data center is located and when it operates. It also depends on which power plants respond, how efficiently the facility removes heat, and whether new demand leads to cleaner generation or extends the use of fossil fuel plants. There is no single energy identity for AI. The same model running in two locations can have a different carbon footprint because the electricity mix is different. The same task can require different amounts of power on different hardware. A well-utilized server may deliver more useful work per watt than a lightly used one. A small model chosen carefully may be far more efficient than sending every request to the largest available model. So what would make AI less power-hungry, without simply making it less useful? The first lever is to improve the chips, especially the movement of data between memory and computation. The second is better software, smaller models, lower numerical precision, smarter routing, and fewer unnecessary calculations. The third is system design, including faster networks, efficient power conversion, and cooling that removes heat with less overhead. The fourth is operational discipline, keeping hardware productively busy, scheduling flexible work when electricity is cleaner or less constrained, and matching the size of the model to the difficulty of the task. There is also a design choice on the user side. Not every problem needs the largest model, the longest chain of reasoning, or a generated video. As AI becomes embedded in more products, developers will increasingly decide when an advanced model creates real value and when a simpler method would do the job with less cost, less delay, and less electricity. That does not mean useful AI should be reduced to the smallest possible system. Some difficult tasks genuinely benefit from more computation. Scientific modeling, drug discovery, weather forecasting, advanced robotics, and complex engineering may justify substantial energy use if the results create enough value. The goal is not zero electricity. The goal is better results for every watt consumed. And that brings us back to the prompt that started the journey. It looked like a few words on a screen. Behind it, the request activated a trained mathematical model, moved huge amounts of data, engaged specialized processors, crossed a high-speed network, produced heat, and relied on an entire facility designed never to blink. Multiply that physical process across larger models, richer media, more users, and continuous operation, and the growing demand for electricity is no longer surprising. AI uses so much power because intelligence in software is still physical work in the real world. The impressive part is not that the machine escapes the laws of energy, it is that electricity, silicon, memory, and mathematics can be organized well enough to produce something that feels almost weightless on your screen. The next phase of AI will not be defined only by which model is smartest. It will also be defined by which systems can deliver the most useful intelligence with the least wasted computation, heat, and infrastructure. If you enjoy seeing what is physically happening behind digital technology, subscribe to Parallax Depth. I'll see you in the next one.